Let's say that you're doing your lab with your iLab device and you bump it off your table. Okay, so let's look at a scenario here. Let's draw this out. So let's say this is your table here. All right, you got your floor. All right, this is your floor down here. And then let's say your iLab device is sitting there on the edge of the table, wheel side down, you bump it, and boom, it goes flying off. What's going to happen? It's going to follow a nice parabolic path and end up like that. So let's say your device had an initial velocity that would be in the x direction of 1 meter per second. And let's say the height of your table is 1 meter. Can we determine how far horizontally that iLab device is going to move? Yes, we can. So let's define a couple things. Let's say that this is our origin here. Okay, nice coordinate system already made here. We have a nice vertical, a nice horizontal. So let's say that this is 0. So our initial x position would be right there, would be 0. And then our final x position would be there. So our final position, remember using the constant acceleration model, is the initial position plus the initial velocity in the x direction times the time interval plus 1/2 the acceleration in the x direction times the time squared. So first of all, what do we see here is that acceleration in the x direction, remember, is always 0 for projectile motion. So this whole term here goes to 0. So what are we left with? The final position, what we're looking for, is the initial position, that's our 0. The initial position in the x direction, all right, that's what we defined up here, our 1 meter per second. And times our time interval. So that leaves us with the final position, what we're looking for, is 1 meter per second times the time interval. What's the time interval? Well, we need a little bit more to get that. So the time it takes the iLab device to fall horizontally, or vertically, sorry. So how do we get that? Well, if we look at the constant acceleration model for free fall, we see that the final position is the initial position plus the initial velocity in the y direction times the time interval plus 1/2 the acceleration in the y, right? And that's always just g, right? Gravity. So we'll just put g in there right away, times the time squared. All right, so final position, remember using our coordinate system, it's falling on the ground. That's our defined 0. So 0 is our initial position. Right, we said the table's 1 meter high, plus the initial velocity in the y direction. Well, it's starting up here, basically in the y direction, it's at rest initially. So this whole term then goes to 0. And then we're left with 1/2 gt squared. Okay, if we pop the 1 meter on this side, we're left with 1/2 gt squared on the other side. We'll bring the half to this side to make this 2 meters over g equals t squared. And then let's move all this over here. Then we have the square root of 2 meters over g is the time. All right, so g, remember, is 10 meters per second squared. So then our time is 2 divided by 10, 0.2. Square root of that is about 0.45. So our time is about 0.45 seconds. So it takes about almost half a second for it to fall that 1 meter. All right, now we can plug that in to to what we had earlier. Our final position is 1 meter per second times the time interval. So the final position is 1 meter per second times that 0.45 seconds. All right, our seconds cancel out and we're left with just 1 times 0.45. What am I picking up my calculator for? 0.45 meters. All right, so the distance that it falls horizontally is a 0.45 meters.